Hey everybody, and welcome to another episode of Path of the Dragon's Tail. Hope you're all doing well. I have a little special video for you today, and it's going to go into how we find the doubling sequence within the Fibonacci series and within all of the series. So it's not just Fibonacci, but across all of the different cycles of the infinity series that we've placed in the previous videos. So first things first you have to understand what is the doubling sequence and why is it important. So the doubling sequence, most of you are familiar with technology in relation to the way storage systems like a flash drive or a USB stick, you'll pick up a USB these days and it'll have maybe 1 gigabyte USB or 2 or 4 or 8 gigabytes. Now, if you notice the patterning, if you're looking at these numbers here, it'll go up in increments of 1, then doubles to 2, then doubles to 4, 8, 16, then 32, 64, and so on. And it keeps going up in cycles of duplication of the previous. So in other words, we take the 32 gigabyte drive, we don't have a 50 gigabyte drive. It'll go straight to 64 if you're following it in that manner. The other places that we can observe this is within cell division. We take a single cell organism, it'll split into 2. And then from 2, it'll split and create 4. And then from 4 splits in and creates the 8, which is basically our first cube structure. It's a very bad drawing, but you get the picture. And from 8 becomes 16, then 32. So we're doubling every time. So what the doubling code or the binary code inherently within this structure is these 6 numbers here. It will go 1, 2, 4, 8, and then using digital compression, we get 7 from 16 and 5 from 32. So 3 plus 2 is 5, or minus 8, minus 9, minus 9, minus 9, until we get to a single digit. So 16 minus 9 is 7, or 1 plus 6 is 7. Choose which way you want to work it. Easiest and cheating way is to just take the single digits, and they pretty much do the same thing. Not pretty much, they do. All right, so now that we've established that we have this 6 code, and you see how it repeats. 64 is 10, that's a 1. 128 comes down to 2. It repeats every 6 times. So we have the doubling code. How do we find it within Fibonacci? So when we take the Fibonacci sequence, so if I just take, for argument's sake, we're just going to take this sequence only, okay? And I'm just going to get rid of the rest of you guys. So we flip it around and we have the Fibonacci sequence here. So what we have is 1, 1, 2, 3, 5, 8, and so on. So let's highlight the number 9. If we highlight the number 9 and then we find an alternative to number 3, we want to see the 5. We want to find the 3, the 6, and the 9. So there's another 3 there. And I'm going to circle them here for you. 3. There's another 3 here, and then there's another 9 here. There's the 6. There's the 6. And what you will find is they will fit perfectly onto a 6-pointed diagram. So the 6-pointed star. You see how that diagram fits perfectly on those spots. So now that we've allocated and outlined those spaces, now what I want you to see is the numbers in between the space. So we have 1, 2, 3, 4, 5, 6 spaces between these 6 points. So we've isolated and we've taken those numbers out, and now we're left with these 6 spots. So let's add these numbers together, and we're going to use this page. So I'm just going to pause and flip. Ta-da! There you go. All right, so now that we've got a nice fresh page behind us, we can have a look at this. What's 1 plus 1? Well, that's 2 plus another 2. This one's going to be 4. Now, let's go here. 5 and 8 and 4. So 8, 4, we got 12. We've got 17. So 17 is 8. Okay, haven't got much room there, but there's my 8. 7 plus 1 is 8. 8 plus 8 is 16. So there's my 16. 1 and 6 is 7. 8 and 8 is 16 again. So 16 plus 4 is 20. 5, 6, 7, 23. 2 and 3 is 5. So we have our 5. Now we have here 4 plus 1 is 5. Plus 5, 10. Drop the 0 or minus 9. We have our 1. And then we have 2 plus 3 2 plus 1 is 3, 10, 11. There's my 2. So check it out. We have 1, 2, 4, 8, 7, 5 going in a clockwise manner. So it's pretty interesting to note, right? So now, what happens when we isolate a different number? So we're not going to isolate the 9. Well, how about we isolate the 1? But which one are we going to isolate? Well, here's what's going to happen. There are 5 ones in the Fibonacci sequence. So if we isolate this one, let's see what happens. 1, if we follow this triangle, highlights a 7 and a 4. So we've just found one of our triplets. 1, 7, 4, just not in exact order. And if you don't know what the triplets are, if I just grab my keyboard here, look at the numbers and the way that they outline. 1, 4, and 7, 2, 5, 8, 3, 6, 9. All of you probably have come across already by now, if you follow this work, the understanding of 3, 6, and 9, Nikola Tesla and vice versa. But you may not be familiar with the others, which are 1, 4, 7, 2, 5, 8, and 3, 6, 9, obviously, to complete the triplets. Okay, so these are our triplets, and then we have our binary sequence of 1, 2, 4, 8, 7, 5. And there they are. So we've highlighted 1, and we have in relationship 7 and 4 across the triangle. So what's on the opposite triangle? Well, let's take a look. We've got 2, 5, 8. Would you look at that? There's our 2, 5, 8. There's our 1, 4, 7. If we go around this way, or we go this way, it's 1, 7, 4. If we go this way, it's 5, 2, 8. If we go this way, it's 8, 2, 5, 8, or 8, 2, 5. Depends on which point you want to start at. Either way, we've highlighted these numbers. So by placing this star here, we highlighted the 3, 6, 9. By placing the star here, we've now just found the other 2 triplets within the Fibonacci sequence. So where's the binary sequence? Well, we found that it's here, but there is another way to look at it. So before we get to that point, let's check out what happens with the next one. Well, if we put this here, check out this. We have 1, 1, 1, and we have 8, 8, 8. So now within Fibonacci, we have the 1 and the 8. We have the paired 1 and 8 equal 9. And you see how that happens there. So 1 and 8 are triangulated across from each other. So now let's go. What happens on the next one? Because we can only do the next one. We know what the one after this is going to be. So here we are again. 2, 5, 8, 1, 4, 7. Interestingly enough, we can create exactly 3 different triangular points. We can either highlight the 3, 6, and 9, we can highlight the triplets, the other 2 triplets, or we can highlight the 111 and the 888 within Fibonacci. So we've seen how we got the binary sequence this way. We've seen how we got the triplets by the other triangulation, and we see how we got the pairing of 1 and 8. So where are the other 2 pairs? Where's 2 and 7? Where's 3 and 6? Well, we understand 3 and 6 is within the 3, 6, 9 to a degree, but then where's 4 and 5? Well, this is where the other sequences come in. So when we highlight it in this way now we have the Lucas code, now we have the 336 code, and now we have Fibonacci. So Fibonacci being 3.14. So there's the seed for Fibonacci, and then 213 being the seed for Lucas. And there's pi. So here is the 214, it's around here, 213, sorry, and then Fibonacci is over here, 314. So if we're starting at 314 here, we will generate the Fibonacci code. If we're starting at Lucas 213, we will generate the Lucas 24 code. And then when we align them up, we align the 9s. It's important to understanding. Aligning the 9s across these 3 cycles, we generate the series, the infinity series in a sense, or the for Robert Edward Grant calls these the 4 quartets. So we're understanding that through his work in that way as the 4 quartets, but I want you to understand it as not only the 4 quartets, but also as a series, as almost like a torus. It comes in and then comes back out. So this first 4 points is the first half of the mirror. The opposite half, the rest of the cycle, so to speak, is over here. There's the double 5, 6, 7, and 8. It's the exact flip. So now that we understand that, and now we understand the triangulation, let's have a look at the other numbers. So remember, we found the binary code within the Fibonacci sequence, but we can also find it in the Lucas sequence. 2 plus 2 is 4, 4 is 8. So that's our 8. And so then if we go to the next one, 1 and 7 is 8, and there's my 16. So notice that they've just moved up by a double. See what's happening? So then the next one is going to be a 7. So this is actually my 7 here. So that one means that this is going to be my 5 in Lucas. And let's have a look at it. Okay, so there's my 7. 7 plus 1 is 8. Sorry, I'm in Lucas, my apologies. 5 plus 2 is 7. 7 and 7 is 14. 1 and 4 is 5. You see what's happening? It is exactly 1 degree prior. So instead of going 1, 2, 4, 8, 7, 5, the Lucas sequence is going to start 1 here. Okay, and then it's going to go 1 here, 2, 4, 8, 7, 5. Have a look and you can calculate it yourself. Pause the video. So now, what about Fibonacci? Well, let's look at Fibonacci in the middle. 4 and 4 is 8, plus 8, that's 16. So we have 16 here. Notice 4, 8, 16. We've just gone up another cycle, another interval, when we've lined it up this way. So then this must be 7. Well, 5 and 2 is 7, 14, 4 is 5, sorry. There's my 7, 16. So this one is our 5. 8, 7, 5 between the two. So we have binary coming in just as much as binary going out, coming in this way, coming out this way, across the 6 points, in and out, okay? So if we're following it this way, that means that we have 4, 8, 16. What are we missing? Well, we're missing 32, which would technically be 5. So we've got our 7. We're missing our 5. We're missing our 2. We're missing our 1. So let's see what happens. 4 and 4 will carry 5 and 5. So this must be either a 1 or a 2. 5 and 5 is 10, plus 1, 11. There's my 2. So then you understand that the next one is going to be a 4. So just for your reference, here's my 3, 6, 9. 7, 2 plus 4 is what? 6. 4, 5, 6 plus 7, 13. 1 and 3 is 4. There's my 4. And you see what's happening. So we have our 4. We have our 5, 8, 7. We can see the code generating inside just as much. Now I can pop the other 2 in, but you're going to know what's going to happen anyway. So we're going to fast forward now. So that's just one way of highlighting it. So now, how else can we see the binary sequence through the Fibonacci series and through series 1? And is it only unique to series 1? So I want you to understand something. This sequence is by adding the 3 spaces in between. But there is another way to do it. And I'm going to show you here. If we take the Fibonacci series across these points, and we're triangulating the 3, the 6, the 9, and then we're triangulating the only opposite, as the only unique aspects of these, which is the 111, the 888 within Fibonacci. It will also be the 222 and 777 in Lucas, and then 444, 555 within Fibonacci. When we do this, we space out these numbers here. These are the outside circle numbers, if you will. So you see the big circles around here. So then what happens when I plot these numbers in another way? Well, if I plot these numbers moving ascending, descending, ascending, descending in a sort of wave-like pattern that you find in many things in nature, let's see what happens. We will start at 9 or 0. Fibonacci goes 1, 1, 2, 3, 5. You see how I'm going up, pretending these numbers represent this line. The ones on the outside represent this line. The ones on the inside represent this line. we have 9, 1, 3, 8, 3, 1, 9, 8, 6, 1, 6, 8, 9. So we only have within the circles 3, 6, 9, 1, 8. 1 and 8 we know are paired, and 3, 6, 9 we know are paired. So we have 1 and 8 within Fibonacci. Now, how do we understand Fibonacci? It starts with 1 and 1. There's my seed. But understanding also, if I start at 8 and 8, it will also generate Fibonacci over here. And this is important. I'll get to this in another part. So now that we understand these parts, let's have a look at the numbers here. You've already probably read ahead, but let's go in reverse. 1, 2, 4, 8, 7, 5. Counterclockwise, we have our binary code going counterclockwise on the bottom end. But look at what's happening on the top. 1, 2, 4, 8, 7, 5. And how do we come across this? Well, we have to take Fibonacci and carry it through a 3-pointed curve going in and out across 3 points. So starting off with the middle, or whichever way you want to see it, starting 9 and vice versa, and going in 1, 1, 2, 3, 5. So I prepared this one a while ago, just so that you can see how this correlates across all of them. We're starting at here, 9 representing 0. 1, 1, 2, 3, 5, 8, and so on. Let's look at Lucas. We've already showed you, but let's look at Lucas. 2, 2, 4, 6, 1, 7. Starting at 2, 2. Remember, 2, 1, 3 is over here. Okay, but we start Lucas 2, 2 for the infinity series. Look at the outer edge. 1, 2, and where this dividing line is where we would start the next cycle. 4, 8, 7, 5. There's our doubling sequence. 1, 2, 4, 8, 7, 5. And then it repeats again. Look at the opposite end. 1, 2, 4, 8, 7, 5. It's the same for Lucas. Check it out over here in 3, 6, 9. We have 3, 6, 3, 6, 3, 6 on the outside. And then we only have 3, 6, 9 in the middle. So 9 is the only one in the center. And on the other end, we have 3 and 6. So the 3, 6, 9 code is unique. It only has 8 numbers that cycle. But the other 3 codes in the Infinity Series 1, or the 4 quartet, if you will, they have 24. So we have 8, and then we have 24 across mod 9, or D-space. So looking at Lucas, or Fibonacci, here's our 4, 4 seed. And then looking on the outer edges, we also still have the binary code on the outer edges. So when we map it in this way, we see not only the binary code is by adding these 3 numbers, but also by understanding that this number is relating to this number on the bottom spectrum, the lower spectrum, and this is the upper spectrum. And then in the center, the very middle, is the seed number, its opposite pair, and the numbers 3, 6, and 9. So when we view it in this way, we can see that 3, 6, and 9 are the bridge between the two. And in between the bridges, we have the numbers seed. There's 9, bridging 1, 3, bridging 8. You see what I mean? The bridge gap between the two. So now, when we understand this, we think, okay, well, what's the significance of this? Well, if we understand Fibonacci sequence as only starting at 1 and 1, that just means that we're starting at the absolute lowest area, the lowest point is 1. That's the smallest number that we can start with, besides 0. But we can go 0, 0, 0 for eternity. It's never going to go anywhere. We need the 1. So now understanding that when we take the Fibonacci code, the sequence, and I'm just going to show you this now. So when we look at this sequence, the Infinity Series 1, this is incomplete obviously, but when we look at it in this manner, what we find is we have the Fibonacci sequence starting off with 1, 1. Lucas, we started at 2, 2. Then we have the 3, 3, 6 code. So this code, in a sense, is unique because it only follows across 8 points, not 24. And then we have the 4, 4, which is the Fibonacci. And we understand that they start there, this one starts here, and vice versa. So then 5, 5 is Fibonacci reverse, as you can see right over here. On the opposite end, where are we? Here. 5, 5, 4, 4. 5, 5, 4, 4. They are the exact same code, just reversed. We've already established this. And then the 8, 8 starting seed would also generate the Fibonacci in an exact 180-degree turn. So, not reverse, my apologies, 180-degree turn, still going in a clockwise manner. When this reverses is when we get to the Series 8 code. And when we get to the Series 8 code, it's interesting to understand that the 1 and 8, as I said, are paired. So the Series 8 cycle is actually the reversing of these numbers. It generates the reverse code, but the values are different. So when we understand that the values are different, well, if we think about it in that sense, and we say, okay, well, Fibonacci traditionally starts with 1, 1. Okay, yes, it does. However, Fibonacci can also start with any of the numerical seeds. Take any two numbers across the Fibonacci 24 spoke wheel and put them together and then modular 9 them. They will create the exact same sequence. Don't believe me? Check it out. We know it starts at 1, 1, and we know that when we get to this number 4 here, this is the first of digital compression. So then every number after this point technically is not part of the Fibonacci series in its full totality, if you understand what I mean. So now let's look at the sequence. Let's pretend we start at this 4. 4 plus 3, for example. We're using Fibonacci math. We take the sum of the first and the previous number. Okay, so we need two numbers to start the cycle. 4 plus 3, well, that equals 7. So now we have 7. 7 plus 3 is 10. Would you look at that? The next one's a 1. 10 plus 7 is 17. What's 1 plus 7, everybody? Well, it's 8. And you see what's happening. We're generating the exact same code, but we started from a different seed. So what does that mean? Well, this is not just unique to Fibonacci. This is also inherent within Lucas, within the Fibonacci, and within the 336 code. But the only thing to understand here is that the 336 code, the Lucas code, Fibonacci, and all of these sequences, they all have exactly 24 points, 24 seeds that they represent. And I'll show you that here. So, understanding this now, we have 81 possibilities of seeds. Out of these 81 seed possibilities, and I'll zoom the camera in a little for you, and I'll just bring this down a little. So, a seed of 1 and 1 will generate Fibonacci. And I've highlighted all the Fibonacci seeds in red for you. So then I've outlined, and you can see here that there will be 24. Now the quick and easy way to understand this is that Fibonacci starts with 1, 1. And it is going to have exactly 5 number 1s within the cycle and 5 number 8s in the cycle. And every other number is going to repeat twice. So if you see here, the number 9 is going to repeat only twice in Fibonacci. The number 1 repeats 5 times. 2 will repeat twice. 3 will repeat twice, 4 is twice, 5 is twice, 6 is twice, 7 is twice, 8 is 5 times, because 8's opposite pair is 1. And then if we look at the same thing in Lucas, being in blue, we're going to see the Lucas code will generate 5 numbers starting with 2, and then 5 numbers starting with 7. And then Fibonacci will start 5 numbers of 4 and 5 numbers of 5, and 2 of every other number. So we have 24 possible seeds and 24 possible Fibonacci cycles. Okay, Fibonacci 1, 1 is not unique to 1, 1 Fibonacci. It's just the lowest spectrum of Fibonacci. The absolute highest value that Fibonacci can create is starting from the absolute highest number that we could start off with. So if we look at the red ones, we see that the highest point that Fibonacci could generate, it would be based on the numbers 9 and 8, because we're taking 9 plus 8, okay? And so if we had 8 plus 9, it's actually going to be higher. So you would think it'd be 9 and 8 because we're starting, but it's actually the opposite way around, because we're going to start with 8 plus 9, and that's going to give us 17. But then we're taking 9 to 17, so we're going to be one unit higher by here, because we're going to take 9 to 17. But over here, 9 and 8 is 17, but then we're going to have 8 go into 17. So we're going to be 1 unit behind on these 2 points. So by starting at 8, 9, we are going to generate the highest possible scenario of Fibonacci 1. And then the same rule applies for Lucas, and then the same rule applies for Fibonacci. So out of all of these, what you might be aware of is that, okay, if we take 24 plus 24 plus 24, and then we understand that the 336 code, or the 369 code I'll call it, only has 8 seeds. There's 2, there's nothing in the 1, nothing in the 2, there are 3 3s, there are 3 6s, and there are only 2 9s. So we have 8. 6 plus 2 is 8. So we have 24 plus 24 plus 24 plus 8 equals 80. But there's 81 divisions. There's 81 seeds. The only one missing is 99. And the only way to get 99 is to start the sequence at 99. And so this is where the last of the series comes in. The 9 is not only at the beginning, because it also represents 0, but it is also at the end, because it also represents itself. 9 can only reflect itself and the number it starts with. So if you're multiplying anything by 9, it will equal 9. But even in this case, starting with 9 and 9, because we're going up in increments of 9, the last cycle will only be 9. It is, in a sense, even though using addition, because we're only adding 9 with 9, we're not going to get any other number in that final cycle. So this is the end of the cycle. And then it begins again at 1. You see what I mean? So we already covered in the videos prior, where we went in and we understand that not only do we have within the series 1, we have the Vedic square numbers. So we have the ascending numbers of 1, 2, 3, 4, 5, 6, 7, 8, 9, which is the mathematical starting point of the 1 times table. The 2 times table compresses to 2, 4, 6, 8, 1, 3, 7, 1, 3, 5, 7, 9. And then the 3 times table inherently creates 3, 6, 9 repeatingly. And then the 4 and 5 times table create this unique 4 code or 5 code. So 5, 1, 6, 2, 7 is the 5 cycle. And then 4, 8, 3, 7, 2, 6, 1, 5, 9 is the 4 times table in Vedic digital compression. And so we have this inherent within series 1. What I want you to now understand is that this is not just apparent on series 1, but across all series. So if we take out Fibonacci 1, so that's why I call it Fibonacci, even though Lucas and Fibonacci are all part of, are all different in a sense in the mathematical world, to me, they are the exact same series. They are part of a set, a complete set. And so that complete set is held together by the 9. Then when we understand series 2, it is the exact same. Look at the sequence. 1, 2, 3, 4, 5, 6, 7, 8, 9. 2, 4, 6, 8, 1, 3, 5, 7, 9. I don't have to keep going because you can see it for yourself. We have the Vedic square within. Not only do we have the Vedic square, but we also, when we use that same triangulation that we saw earlier, we're highlighting the numbers 9, 3, and 6, and 9 as well. And we're highlighting the numbers in the middle will also give us the binary sequence as well. And so this is important to understand on top of this. We also have in the 2, 7, we have 24 seeds. Now I haven't gone into understanding all the seeds, but you can see this across the 4 and 5, where if we line up the 4 and 5 in such a way where all the 9s are lined up, checking it out, 1, 2, 3, 4, 5, 6, 7, 8, 9, 4, 8, 3, 7, 2, 6, 1, 5. 8, 7, 6, 5, 4, 3, 2, 1. We've got the Vedic square again. The only time that it doesn't happen is within the 3, 6 wheel. Because the 3, 6 wheel will only show the seed we started with and then the numbers 3, 6, and 9. So 1 will only go 1, 3, 1, 6, 1, 9. It will repeat infinitely. 2, 2, 6, 2, 3, 2, 9, 3, and so on and so on. So within this structure, we start to have less and less of the seeds. We only have the seeds starting with 1 and either 3, 6, or 9. Then we have 2 with 3, 6, or 9, and 3, 4, 5, 6, 7, 8, all of them only with the numbers 3, 6, and 9, but never within any other number. So we don't have as many starting seeds when we're multiplying by 3. So understanding, remember going back to that video of how we come across these series, we're taking, for example, in series 3, we're taking the number, we're multiplying it by 3, and then we're adding the previous number. And that's how we generate this sequence. So when we do this, as I said, whatever seed we start with, we will generate the opposite seed. So understanding that it's flanking each one. And so that concludes our video for you today. So understanding all of this and how it sort of correlates together, don't mind my little crazy drawing there, but bringing it into this nice beautiful little equation of the way that we can not only see it when we structure the triangles, but we can also see it in the form of how it's depicted when we isolate the fruit of life, for example, in this way. And when we triangulate the fruit of life with the seed and the 369 across any of the cycles, whether it be Lucas, Fibonacci, or vice versa, by understanding these triangulation points with these triangulation points, we can reveal within Metatron's cube the starting positions of the 12 points of the dodecahedron within the center. And that reveals the dodecahedron to some degree, but then we have to add and understand how to intersect the other lines to reveal it even further. And that's where I'm going to leave you. And so I hope you enjoyed that video. I know it was a lot of information there, but I wanted to show you all of the different variations of what we can find through these cycles in time and through these cycles of numbers and how they correlate to each other. Not only, as you see, we have the triplets, we have the doubling sequence in many different ways, and we also have the development of the, I lost my words here, but the pairing of the numbers. So the pairing of the numbers in relationship to their polar opposite, 1 and 8, 2 and 7, 3 and 6, 4 and 5. And then understanding the relationship that 3, 6 and 9 has with the other numbers. 3, 6 and 9 are very unique to themselves. They work within their own triplet. And then 2, 5 and 8 tend to work within their own triplet as well. And 1, 4 and 7 works within its own triplet. But you notice that within the other two triplets, 2, 5 and 8, none of them are paired numbers. They're the exact separations of each other. 2 is paired with 7, 5 is paired with 4, and 8 is paired with 1. And it's the opposite triplet that they need to complete themselves. So if you were to look at it in the sense of yin and yang, if we have 1, 4, and 7 as either yin or yang, you can pick whichever one you want it to represent for now, and the opposite is the 2, 5, 8 is yin or vice versa, we have yin, we have yang, and then what combines them together? So we have the separation, but it's the 3, 6, and 9 that cover the central path and combine the two together. And that's important to understand. So, hope you enjoyed the video again, and I'll catch you all in the next one. Have a good week.